say the proposition, we've got that possible under the proof. The philosophy up there was, instead of directly trying to find a convergent subsequence, we'll use this reformulation of subsequences. And guess the citation is 5.2.1. 5.0. 5.2.1. It suffices to show that for all epsilon bigger than 0, for all big M, there exists a little m bigger than big M with so there's the thing we need. And it's before going to the models, let's go and make sure the motivation for what happens next. So eventually I want to get a thing in the sequence that's pretty close to lim soup. So lim soup, by its very formulation, is really close to a subsequential limit. In that you can get this distance to be less than epsilon. Well, if this is a subsequential limit, can I find a choice for xn that's pretty close to it?
Wait, what is xn again?
Xn is the sequencing question.
Okay.
S is the lim soup.
Yep.
I need to get xn to be close to S. As one basket, precisely. But I need xn to be close to S. I know that there is a subsequential limit that's close to S by the reformulation of supremum. So
How do you choose big M, right? That would be what is close to supremum.
Well, not there. There is no big. We don't need to choose the M in this. M. Okay, that's sorry. Yeah. Yes, we also don't get to choose big M. We have to consider every big M.
Okay.
But so let's think about that. So no matter how big M is, this x is a subsequential limit. Can I find some terms in the sequence with little m bigger than big M and the sequence close to that subsequential limit?
Yeah.
Yeah, that's what subsequential limits mean. So there's like the picture of the proof. And let's see, so it looks like there are like two steps. So I think I really want this difference to be like epsilon over 2. And that difference to be epsilon over 2. So that change will be made up there in a moment. Well, let's write down the next thing. So since S is equal to the supremum of the set of all indecisive. It's the supremum of the set of subsequential limits.
Okay.
So it's the supremum on L where L is the set of subsequential limits of xn. That's not a full sentence yet. Because of that, there is some x in L, i.e. a subsequential limit, such that s minus epsilon less than x less than or equal to the supremum. So maybe right here there should be a people happy now? Alright, and I think that even though I just said I want to left the epsilon over 2, I wrote epsilon. But you can still put an epsilon over 2 there, right? Yeah, that could be any positive number. So in the notes, that puts us I know x is a subsequential limit. In fact, maybe I'll deviate from what's up there just a little bit. Gesundheit. X is a subsequential limit. So this same theorem tells me something. So by theorem 5.2.1, what can I conclude? Possibly by looking back at the theorem. Yeah.
That you can get x sub n, your whole sequence to be arbitrarily close to s.
That's my goal. But x is the thing that I know is a subsequential limit.
Oh.
So I can get that as small as I want.
Yeah.
And maybe we'll just parse things out. So what does this theorem say? Well, it says that, right? But with x instead of s, because I know it's a subsequential limit. So I'm using theorem 5.2.1 two different ways. It's an if and only if theorem. Here I'm using that theorem 5.2.1 implies subsequential limit. Here I'm using theorem 5.2.1 as proof of a subsequential limit. And maybe I'll put the qualifier in there. There's some little n bigger than big N with absolute value x of n minus x as small as I want. And how small do you think I want it?
Given the nature of the problem, I'd say epsilon over 2.
That seems reasonable. We'll see if it works out. If it doesn't, then we'll revise. All right, so maybe I'll indicate what I'm doing in the notes. So if you like, I am skipping this, and instead by theorem 5.2.1, as x is a subsequential limit, there is some little n bigger than big M such that absolute value of x minus s is less than epsilon over 2. All right, so now what do we have to do? I'll number these two things. No, that's the second one, so that needs to be 2. Can I combine those two things to get x of n to be close to s instead? Yeah.
What is it on the paper? It's supposed to be x not s squared? Or
No, I did the same thing as I did on the board, didn't I? Yeah, if I already had this, I'd be done. Oh, and it should be x sub n. Thank you for pointing that out. All right, there we are. So let's try to manipulate these two things. And maybe I'll do some stuff on the board. I'll move one panel farther to the side because this is going to be vaguely scratchable. Then we'll put it on the board, then we'll put it on the paper. All right, so here are the things I have. S minus epsilon less than x is less than s. And I have xn minus x less than epsilon over 2. And my eventual goal is going to be xn minus s is less than epsilon. So let's try to, I don't know, what would you guys like to do if you wanted to, if you had knew these, you wanted that? What would you do?
Well, I think we've got that. Can we just start filling in from 1 to get to something that looks sort of like 2? So like we multiply by -1 and everything, and then we just add on a x sub n. That's possible?
Cool. Which particular one do you want to start with?
Negative one.
This one?
Yeah.
And then you want to multiply that by. Let's see what that gets us. So it's going to give us negative x less than negative x less than negative s plus epsilon. Okay. Yeah.
Continuing with the stratagem, I would add an x sub n onto that x there. Might possibly have to go on, but
Except that. Okay. So maybe I'll suggest that. So it sounds like you're trying to go from here to there.
yeah.
These are the things you already know.
Oh.
You want to go from knowing these two things to this thing. This is the
Oh, okay.
So, with that slight revision, what would you want to do?
Is there a way that we could use contraction to add a multiple of 2 into the non?
It might, but I think it's harder than you're making it more complicated than it needs to be.
Can we just arbitrarily look through it?
Yeah, we could.
We talked about that.
Yeah, like, we could. I don't think we need to, though. Maybe I'll suggest this. There are some absolute values. Let's just get rid of the absolute values.
Yeah.
What would this become if you got rid of the absolute values in the way that's correct?
X sub n minus x is between negative epsilon over 2 and epsilon over 2.
All right, and let's revise the goal also. What does this become if we get rid of the epsilons?
X sub n minus s is between epsilon and negative epsilon.
All right. So I have to go from here, and we haven't used 1 yet, and that's our goal.
Not sure how to apply 1 here.
Yeah, we could use, why can't I pick the words now? Transitivity.
Yeah, that's a good idea.
And we could add s. Here's my thinking. If we add s to each side, it would be transitivity to, or I say each side, but if we add s, it would be s minus epsilon less than x and minus s. Did I say s? My brain is fried.
No,
Yeah,
I
x
think
and
it's
is less than
yeah.
s plus epsilon, and then from there we have
So could you do the same type of thing to this?
Yes.
Yeah, I guess it would be adding x to everything inside instead of s.
Yeah.
Minus x. Cool. All right. Thank you.
Okay.
And so we can use transitivity to say that, the s minus epsilon is, oh, sorry, my brain. Yeah, that's
Oh.
good, of course. So, yep. Less than, the negative epsilon over 2 plus x.
Mm-hmm.
That part.
So s minus epsilon over 2 minus epsilon over 2 is less than this.
Yeah.
Oh, cool. Does this imply that?
Yeah.
All right, so a proof is on the board now. It's slightly unreadable. But, I mean, we can now follow the arrows and put the ones. So let's do that. So, looks like there's where we want to start. So, minus epsilon over 2 is less than, you know, I think we could jump straight to here and that would be okay, right?
Yeah.
So, x minus epsilon over 2 is less than xn is less than x plus epsilon over 2. The next thing we did is we used this condition. Since s is less, nope, s minus epsilon over 2 is less than x is less than or equal to s, what do we get? We get s minus epsilon is less than x minus epsilon over 2 is less than xn is less than x plus epsilon over 2 less than or equal to s plus epsilon over 2. Maybe I'll stick an extra less than s plus epsilon. And so now, like, what do you do from there? You turn that into this. And then you can say, properties of absolute value, let me turn that into this. So, s minus epsilon less than xn less than s plus epsilon, so that absolute value of s minus xn is less than epsilon, which is what we wanted to get. People feel pretty okay so far? Right, so all those things I wrote, well, just this, right? And so now I guess the concluding sentence. We've now proved that for any epsilon and any big M, we have produced a natural number, little n, bigger than big N, such that absolute value of xn minus s is less than epsilon. By the reformulation of the subsequential limit, theorem 5.2.1, we conclude that s is a subsequential limit of xn. That argument feel pretty okay?
The talking through seems all right, but the writing through not so much.
Yeah.
Yeah, I think I'm still missing the third line down. Since s minus epsilon over 2 less than x less than or equal to s, that expression.
Yeah, let's talk through where that's coming from. So maybe I'll try to color code some things. So this much anyway is exactly that, right? I know that s minus epsilon is less than x. So s minus epsilon over 2. So s minus epsilon over 2 minus epsilon over 2 is less than this. Does that feel okay?
Yeah.
I know that x is less than or equal to s. So x plus epsilon over 2 should be less than or equal to s plus epsilon over 2. And instead of adding epsilon over 2, you can add epsilon. That's obviously true, and the reason you want that is so you can get this. Yeah.
I'm having a little trouble seeing this one. Could we put that again on a number line on the board for a second, just so I can soak that in? I don't know.
Sure. So I know right now that there's xn. It is between
x plus epsilon over 2 and x minus epsilon over 2. I know that s minus epsilon over 2 is less than x, which means that s minus epsilon is less than x minus epsilon over 2. So s minus epsilon must be over here.
Okay.
I know that x is less than or equal to s. So s plus epsilon over 2 must be to the right of x plus epsilon over 2. Maybe more color coding. And instead of adding epsilon over 2, you could add epsilon. That would make it a little bit bigger. That help?
I think so. And so, oh, it's put in an epsilon of the 2, so that, oh, okay, all right, cool. Yeah.
Awesome. All right. So s itself is a subsequential limit of xn, which it kind of, like that's really a satisfying thing to see, right? So this is the supremum of the set of subsequential limits. Since it is actually an honest-to-God subsequential limit, that means it's actually like the biggest subsequential limit. Right? Not every set has a biggest element. The set of subsequential limits does. That feels pretty okay? Nice. The last claim left in this particular notebook is the following. Let xn be a bounded sequence, and s be the limit superior of xn. It follows that for any epsilon bigger than 0, there is some big N such that for all little n bigger than big N, xn is less than s plus epsilon. So that sounds a little bit like the definition of the limit, right? Right up until the very end. Like if this were actually the limit, then this would want to be like
Xn minus 0 or something?
Like that's the thing you would actually want there if it was the limit.
Oh, yeah.
So you're getting at a single subsequential limit and then doing some stuff. But the fact that it's a subsequential limit doesn't give you a result for all n. It'll give you for infinitely many n's, you'll get that inequality. But not all of them. So I think you need a slightly different idea.
So let's go and try to prove this. And I think the way that I'm going to try to proceed is by contradiction. I'll assume that this thing, that s is the limit superior of xn. I'll assume the negation of that statement. And I'll try to come up with a subsequence that gives me a contradiction. So let's try to play that game. All right. So let xn be a bounded sequence. Let s be the limit superior of xn. For the sake of contradiction, let's suppose not the thing we want to show. Let's suppose not for all epsilon there exists a big N. Is it called big N? Yeah. Such that for all little n bigger than big N, xn is less than s plus epsilon.
Is it epsilon greater than 0? Or is it,
Oh, yeah, it better be greater than 0, otherwise it's way too strong. Yeah, otherwise nothing would satisfy it. Because you could take epsilon to be negative 25 trillion. And then you would just result in the terms of the sequence have to be super negative.
Nice.
Which isn't what we want. All right, so there's the thing that I am assuming for the sake of contradiction. Does that look like something that you know how to negate like the back of your hand? Except what does it mean to negate the back of your hand? I don't know. That's something that you know how to negate. Let's negate it. Universal will become in there exists. So there is some epsilon bigger than 0, such that existential becomes a universal for all n. There exists a little n bigger than big N, and I'm giving myself that space because I'm going to play this same game where I think of little n as being a function. So that little n is allowed to depend on the choice of big N.
Yes.
So epsilon's conjured up at the beginning of the day. It is now a fixed constant through the rest of the statement. For every big N, I can come up with a choice of little n that depends on big N. So I'll think of this as being a function, such that, and then I get to negate this. People feel pretty good?
Yes.
So here's a philosophy that we've used a few times. That looks like I have a thing that is true infinitely many times. That means I can come up with a subsequence on which it's true. And, well, here it is. Let's let n sub k be defined by the core formulation that we've seen many, many times now. Then you already know how to show that n k is strictly increasing. I think I had to go through that work like 5 times in homework. You also know why this inequality will now hold for x sub n sub k, because I had you prove basically exactly that like 5 times in homework. So, what do you get? Consider any k. By the very definition of n sub k, I get that x sub n sub k bigger than or equal to s plus epsilon. And that's true for every k. The original sequence was bounded. Is a subsequence of a bounded sequence automatically bounded?
Yes.
Yeah, that's something that I had you prove. I think maybe twice. I think maybe I snuck it into another proposition where I didn't let you cite something that it was bounded and I made you prove it again.
Oh my god.
So the point is that x sub n sub k is a subsequence which now has a property. I don't know that it converges yet. Can I take a further subsequence to make it converge?
Yes.
By the Bolzano-Weierstrass theorem. So by the Bolzano-Weierstrass theorem, there is a convergent subsequence of x sub n sub k. It's a subsequence of x sub n sub k, so I'll call it x sub n sub k sub j. J is now the independent variable. And so the point is, when you play this take a subsequence game, you can make your life better at each step. And at no point do you make your life worse. You still have all the previous assumptions, yeah.
Normally, I assume if you're taking some sort of subsection or something, you get some form of loss of generality because you're cutting something else out. Is that not the case because subsequences can be the whole sequence?
No, we are losing information each time.
Oh, crap.
But it's okay from the point of view of what we're doing because we're only trying to prove something about the lim suit, which is something about subsequences.
Okay.
So we're coming up with a subsequence, and each time we take a subsequence, we lose some information. But a single subsequence doing something bad will give us the contradiction.
Okay.
Even if it's a subsequence of a subsequence of a subsequence of a subsequence.
Because our tools apply to all subsequences.
Yeah.
Okay.
Nice. So, here's the inequality we have for every k. K sub j is still a choice of k. So x sub n sub k sub j is bigger than or equal to s plus epsilon. But this sucker converges. So I can take the limit of both sides now, because the limit of both sides actually exists. So the limit as j goes to infinity of x sub n sub k sub j is bigger than or equal to s plus epsilon, which coincidentally is bigger than s.
Oh, huh.
And I guess I'm writing right there that this is a contradiction. Why is that a contradiction?
Because then it says that the limit supremum, or whatever, the suplim, whatever it is bigger than, what we're looking for diagram.
Yeah. So the limit superior is supposed to be like the biggest subsequential limit. Hey, look, I just found a subsequential limit much bigger than it. There's the contradiction. And hopefully that's roughly what is written. This contradicts the fact that S is an upper bound on the set of subsequential limits of xn. So I get to conclude that the thing that I assume for the sake of contradiction must be false. So this not statement is false. So the thing on the inside must be true. So it follows then that for all epsilon bigger than 0, there exists a trace of big N such that for all little n bigger than big N, x sub n is less than s plus epsilon. How'd that proof feel?
That was kind of fun.
Good.
One quick question.
Yeah.
The s plus epsilon is greater than s. Can you explain that one more time?
Yeah. Is epsilon bigger than 0 by assumption?
Yep.
Yeah. So s plus epsilon is bigger than s because epsilon is bigger than 0.
Okay.
Yeah.
Okay, cool.
So if you like, we took like lots of effort to verify that that is true way back when we talked about inequalities. But now we're just black boxing and we know how inequalities work. I guess that was like, you take the difference between those two things and you say it has to be in the set of positive numbers, which is cool. All right. So it's clear now that with 15 minutes left, I'm not going to get through the stuff actually on the schedule for today. Which, isn't surprising. I seem to have a very slim grasp on how time works in this class. Let's get started in on the next section anyway. I think that it will feel much more concrete.
Excellent.
So we have lots of powerful tools to think about sequences. What's a thing that's built on top of sequences? Series? Let's talk about series. A series is something like that. So how do you make sense of what on earth that even means? Well, here's the definition. Given a sequence A sub k, define a sequence of partial sums by that formula. S sub n is the sequence of partial sums of this series. It's the sum from k equals 1 to n of ak. So if the infinite series is supposed to be add up all of the ak's, we'll add up like n of them. I know how to add up finitely many things. Yeah.
So I'm visualizing sort of an onion with our tools right now, right? So at the very center, we kind of have set theory.
Sure.
That's building up our sequences, and now that's working to build up our series we're going for. Is that a correct way of thinking about that?
I think that's not unreasonable. Maybe there's an intermediate layer where we build the real set of real numbers on top of set theory.
Oh, yeah.
So depends on how far down the onion you want to go.
Excellent. Sorry, it just helps me think about it.
No, that's good. So yeah, we're building this on top of everything we know about sequences already, because there's a sequence we can study. I'll say the series converges to a number L if, well, what do you think? I should take like a limit of Sn. That probably gives me like what the series should be. Does that make sense? Nice. A series does, so that's what it would mean for a series to converge. A series converges if the sequence of partial sums converges. What do you think it should mean for a series to diverge?
Is that the limit of S sub n or A sub n?
S sub n.
S sub. Oh, there it is. Okay.
Yeah, which of course it has to be, right? Otherwise, you wouldn't be adding up all the terms of the sequence. You would be just seeing where the terms of the sequence go. You need to, right? So, if you want to unpackage notation more, that's the same as the limit as n goes to infinity of the sum from k equals 1 to n ak equals L. That make sense? And that's what it should be, right? So you want to see what happens when you add up all of the terms. You can't add up infinitely many things all at once. But you can add up like 10 trillion things all at once. And then like take the limit as 10 trillion gets bigger. So that's what it means to converge. What do you think it should mean for a sequence to a series to fail to converge?
Does that mean that does not settle on any number at all?
Yeah. So I guess S sub n just diverges. That seems like a reasonable definition, I hope. A series diverges if the corresponding sequence of partial sums diverges. A series diverges to infinity, or minus infinity if you like. What should that mean?
When S sub n diverges to such a place?
Yeah. But hopefully that definition is just like what you would intuit anyway. There are certain circumstances when you like need different definitions because you have some series that like you really think does converge, but it technically doesn't. So then you can come up with different notions like oval summation or Cesaro convergence, which are not things that I'll explicitly talk about in this class. But there are ways of weakening what convergence means, which is useful in some circumstances.
Okay.
If anyone wants to read about that, I have a reasonable little book to lend you. But let's keep on going. So, what does this mean? This means if you want to say absolutely anything about convergence of a series, you just need to say something about convergence of a sequence. We know how to say things about convergence of sequences. Let's just see this in an example. Here are some series. So let's suppose that this series converges to A, that series converges to B, C is a real number. Then, the sum of all the AKs plus BKs should probably converge to A plus B. You buy that? You multiply every term of a series by a number C. You should multiply the series by C. Let's prove that. And I'll just build this proof on top of what I already know about sequences. So, I'm going to prove it for the sum. So, let's give the setup. Let's let AK and BK be sequences, A and B be numbers. I get to know that the sum of AKs, the series of AKs is A, the infinite series of the BKs is B. And maybe I'll, in the margins, try to motivate what I want to show. I want to show the infinite sum of all the AKs plus BKs is equal to A plus B. So that means I want to show something about a sequence of partial sums converging. So I really want to show that the limit of that. I shouldn't actually write in the space that I have set aside for the proof. And there should be an n there. So there's the same thing that I want to show. The sum from k equals 1 to n is... Well, maybe I should just ask. Is what I have just written actually readable? Is it not?
Yeah,
Okay.
the end's a little...
Yeah, but okay. But you know it should be an n.
Yeah.
That's the main thing. Nice. Is addition of finitely many things commutative?
Yes.
Yeah, so instead of adding A1 plus B1, A2 plus B2, A3 plus B3, A4 plus A4, I could add up all the A's, then add up all the B's.
Yeah.
Can't do that with a series directly because I don't know if adding up infinitely many things commutes, but I do know that adding up finitely many things commutes. So I can get away with instead computing the limit of the sum from 1 to n of ak, adding that to the sum from 1 to n of bk is a plus b. By that? Oh, neat. But the sum of all of the ak's from 1 to n, if I just look at that first term and take n to infinity, that gives me a by assumption. That gives me b by assumption. Oh, cool. So, in some sense, I'm at a place where I'm happy in terms of the want to shows. The want to show is now something that's manifestly true. Now let's just add the wads to explain that. Alright, so let's take some sequences of partial sums. So let's let Sn and Tn be the sequences of partial sums for these series. So I guess that means Sn should be the sum of the ak's. Sum k equals 1 to n of ak. Tn is the sum from k equals 1 to n of the bk's. By assumption, where does S sub n converge? Where does Tn converge? B. I want to show something about the sequence of partial sums for ak plus bk. So let's let Rn be the sum from k equals 1 to n of ak plus bk, be the sequence of partial sums for the ak's plus bk's. I need to show that Rn converges to a plus b. That's what I need to show. And let's try to show that. Let's do it by just exploring what Rn is. So Rn is that sum. If I expand it out, and that's to go from there to there, we use commutativity. And this time we're like going in the opposite direction. So how could you rewrite that?
Okay.
Yeah.
A1 plus A2 plus A3
Yeah.
dot dot, and then B1 plus B2 plus.
All right. So, in summation notation, this is the sum of the ak's from k equals 1 to n. Here I see the sum of the bk's from k equals 1 to n. I already have a definition for that. What's the thing that I've already given that name to? Sn. So, let's check this out. Here's the conclusion. Rn, the thing whose limit I want to take, is equal to Sn plus Tn. Do I know what the limit of Sn is? Sure do, it's A. Do I know what the limit of Tn is? Sure do, it's B. So, are there like limit laws that just finish the proof for me? Yeah, nice. So I didn't even have to pull out any epsilons or anything. So by additivity of limits, this means that Rn converges to A plus B. We've just shown that the sequence of partial sums for this series converges to A plus B, so the infinite series is A plus B. Yeah. Yeah. Yeah.
So I'm looking at the series here, and I'm struggling to see where we come up with like the limit as n goes to infinity, because these are still infinite series, right?
Mm-hmm.
And we're taking a finite number of them and then saying they converge. How do we do that?
So the bit where all of the limits happen, all of the limit as n goes to infinity magic, happens in this line. So let's maybe write out that line a little bit more.
Okay.
So the limit of Rn, that's the same as the limit of Sn plus Tn. And the limit of Tn, that's the same as the limit of Sn plus Tn. And the limit of Tn, that's the same as the limit of Sn plus Tn. And the limit of Tn, that's the same as the limit of Sn plus Tn. And the limit of Sn plus Tn, that's the same as the limit of Sn plus Tn. And the limit of Sn plus Tn, that's the same as the limit of Sn plus Tn. And the limit of Sn plus Tn, that's the same as the limit of Sn plus Tn. And the limit of Sn plus Tn, that's the same as the limit of Sn plus Tn. And the limit of Sn plus Tn, that's the same as the limit of Sn plus Tn. And the limit of Sn plus Tn, that's the same as the limit of Sn plus Tn. And the limit of Sn plus Tn, that's the same as the limit of Sn plus Tn. And the limit of Sn plus Tn, that's the same as the limit of Sn plus Tn. And the limit of Sn plus Tn, that's the same as the limit of Sn plus Tn Do I know what the limit of S, well, does Sn have a limit?
Yes.
Does Tn have a limit?
Yes.
So by additivity of limits, I can rewrite this as the limit of Sn plus the limit of Tn. Do I already know what the limit of Sn is?
Okay, yes. All right, there we go.
Yeah, so I've kind of put the complicated bit where you like take n to infinity. I've just used limit laws to do it.
Okay. So we essentially break it up into some finite number first, then we finagle it into a form that we like, and then we take the limit of that form that we made as we take our parameter going to infinity. Which by limit laws we then break up algebraically, and then it falls through to the answer one.
And that's the way to think of a lot of things involving series. Think
Okay.
about the sequence of partial sums. Try to get that sequence to be a sequence that you can prove something about. As soon as you've done that, you know something, you know something about the series.
Excellent.
Cool. So, with my 2 minutes approximately, let's just say some things that are still in here. So there are very few series you can actually compute on the nose using reasonable techniques. One of them is this series, the geometric series, which you remember from Calculus 1. We'll prove that. It won't be hard. It'll be super easy. We'll build it on top of this lemma, which can be proven using induction, which I think maybe I've left as a homework for you. But it's not a hard homework. The next sort of series that is reasonable to compute the limit of are the so-called telescoping series. If you can realize your series as something that looks like a bunch of difference of consecutive terms, and those terms converge to something, you can compute the infinite series. And we'll give the proof of that. It'll be pretty easy. You can use that to take things that don't look like they're telescoping series and turn them into telescoping series to get something like that to converge. Yeah.
This kind of, the telescoping series, I just wonder if my intuition's on the right track. It looks a lot like the series equivalent of the Cauchy criteria for sequences. Because you're taking a difference of the ones, right? And then as long as it keeps going.
If you said contractive, I'd be more prone to agree.
Okay.
Sorry, Cauchy isn't just consecutive terms. It's any n and any m, as long as n and m are big.
Okay.
Contractive is something that's about consecutive terms.
Okay. All right. Cool.
And we'll do that next time. And then we'll start building something that hopefully you'll all find satisfying by your memory from Calc 2. We'll prove the comparison test.
Oh, boy.
And the truth is, you've already gone through the proof of the comparison test like 3 times in this class.
Oh, okay.
Because you remember a few times when I've had you prove that some like series converge, like some very explicit series? If you stare at the proof that you went through to do that, you will extract a proof of the comparison test. But we will actually do it. And I'm well past time, so I'm going to stop now.
Professor, I have one last
We gotta
question.
do the
Yeah.
homework for tonight.
So it's on Google.
Yeah, we were working on it.
No, I was studying E&M.
Okay.
I got caught up. I got a test today that I don't know
I
how
feel
that's
like
going
I
to
kind
go.
of know
But
how to do it, but I don't. It's more like I'm writing words and I don't understand
You want to work on it?
concrete like ideas.
Okay.
So I kind of got the first part, which is like showing that it's a strictly increasing series. I know that this is in like A7, so it should like.
Yeah. So, I think there's a useful thing to write down. I want to show absolute value of the difference. We maybe should move out of here before the next class actually gets in here. Is the function called n of something?
N of k.
Okay.
Yeah.
So here we see n sub a thing plus 1. N sub a thing plus 1 is f of n sub that thing. But I think if we want to continue this conversation, we should probably go upstairs before I start lecturing at you guys about the content of the class that I'm teaching before your class. This board is an absolute disaster. Whew.